to introduce myself, I'm Lindsay White. I'm one of the science executive in the Blue Economy CRC and hosting this, our second webinar on machine learning. I hope it's going to be a very interesting one. I'm sure it will. We're going to have two parts today. Our first part is going to be about machine learning applied to wave prediction. It's going to be presented by Mathieu Cocho from Carnegie Clean Energy. Matt is an ocean engineer. He's got experience in the marine renewable energy across design, certification, operation, and data analysis fields. And I'm going to throw it directly over to Matt to take over your screens, and away you go. Thank you, Matt.
Hi everyone, and thanks Lindsay for the introduction. I'm just going to share my screen so you guys can see my presentation. Go full screen. Okay, so I hope you can see this. Today's presentation is about some of the work Carnegie Clean Energy has been doing over the past year or so, and in particular about the machine learning wave predictor we've developed. I'll start off with talking a little bit about who Carnegie are and about a little bit about our technology. Then move on to the steps we took to develop the wave predictor, and then dive into some more technical details about the wave predictor and some of the results that I can share. So let's get started. So Carnegie Clean Energy is an Australian company. We're based in Fremantle in Western Australia. We've been working on the development of our technology for about 15 years. And we're listed on the stock markets, the Australian stock markets, and we've got about 11,000 shareholders. We've got expertise in throughout, I guess, the whole of the development process, running CFD simulations to model our technology, through to running tank testing campaigns, again to validate some of our simulations. All the way to deployment of full-scale systems. And one example of that is in 2015, we deployed an array of 3 of our wave energy converters offshore Garden Island here in Western Australia. So what is CETO? As I mentioned, we've been working on this technology for 15 years. And I guess the purpose of the technology is to capture energy from the waves and turn it into electricity. There has been several iterations of the technology over the years, starting right up with CETO 1, which I won't talk about here because the operating principle is quite different to how CETO operates now. So I'll start with CETO 2, which was really a proof of concept, quite a small system deployed in 2008. In 2011, we deployed CETO 3, which was 8 meters in diameters and mostly capturing the heave motion. Went on to deploy CETO 4 in Marine Island in 2013, and CETO 5 offshore Garden Island. We had actually deployed 3 of those units off Garden Island in 2014 and operated them for a year. And the last iteration of technology is CETO 6, which, as you can see on the image, is different to the previous iteration of the technology. It's that it captures not only heave, but it's got 3 mooring legs in order to be able to capture both heave and surge and increase the amount of power that it is able to capture from the waves. All those units are installed in depths that are greater than 20 meters, but not too far offshore. And what we call the buoyant actuator sits about 2 meters below the surface. And I've got a very short video here to illustrate the working principle of our technology. So as you can see, as waves roll over the system, it sets the buoyant actuator motions, which I guess starts moving in relation with the seabed and the power takeoffs that are located inside those buoyant actuators. There's 3 of them. then are able to capture the relative motion between the unit and the seabed and turn this into electricity. Okay, so that's enough about our technology and the company itself, and let's start talking about the wave predictor itself. And I guess this slide is explaining why we started looking at developing a wave predictor. A little over a year ago, Carnegie set out on the digital development path, and the aim of this is really to drive down our levelized cost of energy, which is essentially how much it costs our technology to produce 1 megawatt hour of energy, and to make our our technology competitive with other sources of renewable energy like offshore wind or solar. One of the key avenues that we've identified as part of this task is the control system of the CETO technology. The reason we are targeting this system is because it is able to, a good control system will increase the amount of power that the technology is able to capture from the waves, and do this at a relatively low cost. So that's a win-win situation for the levelized cost of energy, or LCOE. So once we'd established that, it wasn't long until we realized that most of, if not all of the literature that discusses advanced control of wave energy talks about future knowledge of the waves. And the intuition behind that is quite straightforward. In the same way as if you're on the bike, you're using your eyes to look forward at what's coming up along the road, and you're able to, using this information, you're able to deal with the obstacles that might come up along the way. CETO can do this with future knowledge of the waves. On the other hand, if you're riding your bike blindfolded, you probably can ride it, but you'll have to react really quickly to what you feel is happening. And this is what CETO, the former old control strategy we're using, was doing. It's called spring damper, and it was simply reacting to the waves that CETO was feeling right there and then. Providing future knowledge of the surface elevation to the controller helps improve the efficiency of the control system and how much power is captured. Now, the next question that needs to be answered is, why did we go down the machine learning path? And there's 2 main reasons for that. The first reason is that machine learning is really good at working really fast. All the hard work is done upstream, where you generate data and train your machine learning algorithm. But once you've done all the training, the machine learning is really good at getting data in and outputting results really quickly in a fraction of a second. And that's really seducing from a control perspective, because the controller wants information in real time as it needs to keep operating in real time. So machine learning really here has an advantage over physics-based models, which need to solve the physical equations of wave propagation, which might make real-time operation a challenge. So that was the first reason. The second reason is that machine learning, and in particular neural networks, which is the kind of algorithm we're using for this application, are really good at understanding and learning complex functions and phenomena, which for waves, it means that it's able to predict highly nonlinear waves, complex bathymetry, but also localized side effects like reflection of waves from a nearby island, or diffraction from nearby man-made structures, for example. So these are the 2 reasons why we're going for a machine learning based approach. And to put this back into the bigger picture of the whole controller, where the machine learning wave predictor sits, it sits right upstream of the control process, if you want. As you can see on the little schematic at the bottom of the slide here, the role of the wave predictor is to predict waves at the location of the CETO system 30 seconds into the future. It then feeds this information to what we call a machine learning CFD solver, which is another piece of machine learning software, which I won't talk about today, but its role is to convert the prediction of surface elevation into a prediction of wave forces onto the structure. This information is then fed into the actual controller, whose role it is to optimize the response of the power takeoff to those predicted conditions. So that was to give you an overview of how the whole wave predictor fits into our technology and in its control system. This slide is about how we went about developing the wave predictor. So we started off with quite a simple data set, and the aim of the first step was really to develop a proof of concept. So we generated very simple linear wave data from my laptop. They're quite easy and simple to generate, and we trained the wave predictor on this data set just as a proof of concept. Once we had done that, we went one step further into the actual design of the wave predictor, where we generated a full non-linear wave data set on a supercomputing machine called Magnus, which we accessed through the Pawsey Supercomputing Center. So we generated over several hundred gigs of nonlinear wave data, and used that to train the wave predictor. Once we got confidence that the wave predictor was able to perform accurately, we then decided to go on and validate it on physical wave data. So we just completed in July a campaign of tank testing, where we generated again a full set of wave data, physical this time, and validated our wave predictor on where. And the aim of this was really to prove to ourselves that the wave predictor was able to perform on physical waves, but also be robust against all the imperfection that real world data might show, such as sensor noise or reflection from the walls of the tank. And we're still in the process, getting towards the end of the analysis of this data set, but we're confident now that the wave predictor works on physical data. The next step is then to go on and deploy the wave predictor in the ocean to turn it into a ready product. So a little bit about the actual wave predictor. So as I mentioned, the objective of the wave predictor is to predict waves 30 seconds into the future at the location of the CETO system in all conditions at the deployment site. How it does that is illustrated here by, on this schematic on the bottom right-hand side of the slide. The wave predictor, as I mentioned before, is a neural network, and it needs input data in order to make a prediction. Now, this input data is measurements from upwave wave sensors, which can be either wave buoy or acoustic Doppler current profilers. This data is then fed to the neural network, which has been trained to predict what the surface elevation is going to be at the location of the system over the next 30 seconds. Now, one of the questions that needs to be answered is what is this training that I'm talking about, and how does this work? Well, as with any machine learning algorithm, training requires a lot of data. So the first part is data generation, and that's what I was talking about in the previous slide, where we first generated linear data, then non-linear data, or physical data. The first part is really to generate a data set to be able to train the machine learning algorithm on. What does this data set need to contain? Well, it needs to contain what the input of to the machine learning algorithm, but also the outputs, what we want the machine learning algorithm to output given the input. So the output, the wanted output is also called the label or the truth. Once we've generated these data sets, we go into the training phase where we feed this input data to the machine learning model and look at what it's outputting. But at the beginning of the training, the machine learning model will output rubbish because it hasn't been trained at all. We then compare this output to what we want, or the truth. And this error between the machine learning model and the wanted output is then given to an optimizer whose role it is to tweak and update the parameters of the neural network in order to make its output match the wanted output. The next question is, okay, I've explained what the data set needs to contain and what the training data needs to be like, but really, what is the training data? What do we feed the neural network? And I guess that's a valid question. And one of them might be, you know, how far do you want those wave sensors to be located from the prediction point? Or what information do they need to measure or to remember and feed to the neural network? This is what is called feature engineering. And again, that's a common task in the development of any machine learning algorithm. So the schematic here on the bottom left-hand side of the slide is aimed to explain what data needs to be fed to the neural network in order for it to make a prediction. So if you look at the center graph of this plot here, of this image here, the horizontal axis is time and the vertical axis is space. And what we're trying to do is to predict waves at the location B along the space axis and 30 seconds into the future, which is the tip of the brown arrow here. The blue arrow represents the wave propagation, and the slope of the arrow really represents the speed at which the information is traveling. So if you go back in time along this blue line and get to the point where it intersects with the space axis, this tells you where you need to place the wave sensors in space in order to measure relevant information to predict the waves at point B. Looking at the plot on the left-hand side, this is an example of a case where the sensors are placed too close to the prediction point, and you can see the blue arrow here doesn't meet the tip of the brown arrow, which means the data you're measuring isn't relevant to predict the waves you're trying to predict. Now, in the real ocean, where everyone knows that waves don't travel all at the same speed, but depending on the period of the wave, some might travel faster than others. This means that if we set the distance between the prediction point and the location of the sensor array at a given distance, we also need to be able to look back in time and remember what the waves have done back in time in order to be able to predict those slower waves, which need to be predicted at point B, 30 seconds to the future. So in short, what I just explained here is that the location of the wave sensor array and how far back in time we need to remember what the waves that have been measured is dictated by the speed at which the waves travel, and this needs to be site dependent because not every site around the world has the same wave conditions. A little bit more about feature engineering and some of the studies we ran to define what those parameters needed to be. So the bottom left-hand plot shows on the vertical axis the mean square, so the error, I guess, made by the wave predictor. And the horizontal axis is how far we placed the wave sensors from the prediction point. And each color corresponds to a different wave period. And you can see, pardon me, that the optimal distance, which is shown by the smaller error, varies with the wave period. If you place the sensors too close to the prediction point, the error is high. If you place the sensor too far from the prediction point, the error becomes high again. So there's an optimum point, which is dependent on the wave period. And I guess if you want to be able to predict all waves at one given deployment site, you need to find a compromise as to where you place the sensors. Another question that's interesting to look at is how many sensors do we need to deploy in order to be able to predict the waves? If we're looking at unidirectional waves, or otherwise called long-crested waves, one can imagine that having one sensor located away from the prediction point is enough to resolve the wave field. Now, if you're looking at short-crested waves, or waves coming from an array of directions, one sensor is not enough anymore to resolve the wave field, and you need to deploy an array of them. So that's the question we answered. And the plot on the right-hand side here shows, again, the error made by the wave predictor versus the number of sensors deployed. And what you can see here is that the error decreases as you increase the number of sensors until you reach a certain number where the error plateaus, and that's the optimum number of sensors. Okay. Now, in terms of the performance of the wave predictor, so we've proven that it performs really well on synthetic data. As you can see here on the bottom left-hand plot, this plot shows again the relative error this time made by the wave predictor over the prediction horizon, which in this case is 30 seconds. Each color corresponds to a different wave predictor architecture. And you can see that the best predictor, which is the one we've chosen, on average makes an error that is less than 4% of the significant wave height over the prediction horizon. So that's quite a good accuracy, and we're pleased with these results. In terms of time series, if you look at the bottom right-hand plot, this is trying to show you a visual of what the error looks like. So the blue curve here is what we want the wave predictor to predict. The orange curve represents the prediction made by the wave predictor at 0 seconds into the future, or in other words, now. So the orange curve is purely a spatial prediction from the sensor array to the prediction point. And you can see the error here across the time series is quite small. The green curve shows the prediction of the wave predictor 30 seconds into the future. So this is a spatial and temporal prediction. And again, you can see that the error is quite small. And I've got a short video here, which is another way of visualizing the wave predictor in action, where, oops, sorry, yeah, here we go. Where the blue curve here is the waves that are measured at a given point. And you can see when it reaches 400 seconds, the prediction curve will appear 30 seconds ahead of the blue curve. And what we'd expect is to see the blue curve then overlap over the red predicted surface elevation, which is what is happening here. So this is just to illustrate the accuracy of the wave predictor. Another important point to mention is that the predictor is able to generalize on wave conditions that it hasn't seen in the training set, provided that these conditions are within the envelope of the training set. This is a good finding because it's very likely that once deployed in the ocean, the wave predictor will have to predict waves in conditions that it hasn't been trained on. Okay, the final slide is the presentation is it's just saying that I've put the wave predictor in the context of wave energy here because that's what matters to us, but it really has a broader range of application, and generally speaking, it has application for any, I guess, application that is limited by wave conditions. For example, boarding or outboarding of sea vessels onto platforms or fish farms, or offshore boat lifting. And finally, the point that I will make is, at the moment, we're relying on measurements from wave buoys or ADCPs, but we're also looking at an option which is to rely on measurements from a radar, which will again increase the range of application of the wave predictor, because then this radar can be mounted on moving structures rather than having to rely on a fixed array. This concludes the presentation. I've just got a short video that I would like to share with you. So if you let me quickly switch application that I'm sharing. And this is a video about the wave predictor that just got released. So I'll just stop there.
Carnegie Clean Energy has developed a wave predictor which gives its CETO wave energy converter eyes into the future, using an array of wave sensors and the power of artificial intelligence. The wave predictor is able to predict oncoming waves, allowing CETO to optimize power production when waves are good, or avoid extreme waves during large storms. The wave predictor can also add value in other offshore industries, where knowing the future is synonymous with safety, reliability and success. Carnegie Clean Energy, powering the future.
Okay.
Thank you very much, Matt, for that presentation.
Thank you.
We do have a couple of questions, and we've got a couple of a few minutes, very few minutes before we move on to the second part of our webinar today. I'm not sure if you can see the Q&A, but the top question is around the stationarity of your data.
Can you discuss the stationary data? Was the training data non-stationary? Do you expect real-world data to be non-stationary? So this is a good question. The training data did cover different sea states, as we expect I guess waves to evolve at a given across over time at a given deployment site, and we did capture this in the data set. What we didn't capture is the transition from one sea state to another. As you can imagine, going from a 1 meter sea to a 3 meter sea, you'll have to go through 1.1, 1.2, and so on until you reach a 3 meter sea. So that these transitional periods weren't captured in the data set. But given that we're able to predict on a range of sea states, I don't think that this transition will be an issue for the wave predictor.
Okay.
The next question is, have you had much experience with making prediction using an input of only the wake movement and previous wave forces elevation on the wake? I haven't had experience doing this, but I think this is definitely something we'll be looking at in the future, in particular for applications where you deploy larger arrays. As you can imagine, a unit located at the back of an array will be able to get some information from how the unit located further forward in the array has moved over the past X seconds. And so that's a good question, and definitely something we'll be looking at in the future.
So obviously Matt's talk has produced quite a bit of discussion and some questions that folks would like to discuss, but I'm afraid we're going to have to move on. We're sitting at sort of 5:36 now, or 5:36 in New Zealand. And so we're going to move on to the next part of our presentation. Thank you very much, Matt. And for those of you who would like to take this conversation further, I'd encourage you to use the Blue Economy Connect portal to carry this discussion on. I can see that there's a lot of interest in this.
Thank you very much. Thanks for having us on the presentation, and I'd like to thank all our partners as well who made this work possible.
Thank you very much, Matt. So we're going to move on to part 2, which is around automated visual assessment of benthos using machine learning in aquaculture and environmental monitoring. So this next part will be presented by Myriam Lacharite and Associate Professor Quan Bai. They'll be joined with some panelists at the end who will also help with the Q&A session. So Dr. Scott Hadley, who's an ecosystem modeler, Son Tran from UTAS as well, whose research focuses on theoretical artificial intelligence, and Dr. Mira Park, whose research interests include image processing, computer vision, and deep learning. And I should say that Myriam is from IMAS at the University of Tasmania, and her research is in the applied marine environmental science area. And Quan Bai, who actually hails from my university at AUT, who is now at UTAS, and his research focuses on multi-agent coordination, trust mining, and agent-based modeling for complex systems. So I'd now like to hand it over to Myriam and Quan to carry on the presentation.
Thank you, Lindsay. Yes, so thank you for having us today. I'm gonna start by briefly giving an introduction and rationale background about the project that we recently started here at the University of Tasmania. And then my colleague Chuan will carry on discussing in more details the methods that were actually employed. Next slide, please. So I'm going to start by giving a bit of background on imagery. So as some of you may know, imagery is increasingly used in applied environmental science, and this is in part due to the massive development in satellite imagery over the past few decades. That has seen a boom in that sense. But it's not only about the satellites themselves that has created a revolution in terrestrial remote sensing, but also the cameras that they carry. And this can either be from the regular tri-band camera that everybody has on their cell phone, probably, to much more advanced cameras such as hyperspectral and multispectral cameras that are now available on land and underwater. So very importantly for us, this technology has become increasingly accessible by being increasingly more affordable. And this means that every data point that is collected is increasingly cheaper to collect. So that has led to a large quantity of visual information in the environment now being collected quite routinely. So for example, any survey or a research study could easily accumulate tens of thousands to millions of images. So as you can understand, this can become quite a burden on scientists to be able to process this imagery in a reasonable amount of time to extract the relevant ecological and environmental data out of it. So this has drawn scientists in the past decade or so to using computer vision in particular, and how to extract the information out of these images by recognizing features of interest, particular animals that you're interested, but also deriving relevant feature attributes. What is the animal that you're interested, that you're recognizing, what size and shape? Next slide, please, John. The marine environment in particular has also seen this revolution. So it's not uncommon now to have underwater imagery in coastal system and deep sea systems. Development of autonomous underwater vehicles, for example, remotely operated vehicles, is now widely spread, including in Australia, that has had a very important role in developing this technology. So we've listed here a few applications of how underwater imagery is used in the marine environment, but this is by no means an exhaustive list. So new applications are being developed every single year. That includes biodiversity monitoring, fish identification, abundance for fisheries management, detecting biofouling on infrastructure, debris, waste, and pollution in the water column, and so on. There are clear benefits of using computer vision in that case. For example, if you have very specific features to detect, so as particular species of fish or things that you do not want to see in the vicinity of infrastructure. It does release human resources, allowing people to do things that have less of a tedious task to it. And by doing so, facilitate any objective assessment of what you're looking at, making it more repeatable in time and in space. And that has clear implications for monitoring. It also can facilitate automation, for example, when it's linked to a response system. So with that background, we started thinking about how we could apply these principles, in particular in Tasmania, in aquaculture environmental monitoring. So we developed a case study. Next slide, please, John. Developed a case study in Tasmania, looking at how we could use this technology in the vicinity of an aquaculture site. So to be clear, imagery is currently used in benthic monitoring beneath salmon farms in Tasmania. This is a quantitative analysis that uses ecological indicators and is usually scored manually by experts. A key indicator of interest is the bacterium Vegetoa, which we're going to talk about today. This is a key indicator. Why? Because it responds to low oxygen environments. So its presence and abundance does indicate that there could be an impact from aquaculture activities. So it is linked to environmental compliance. Currently, the accuracy of the assessment is widely expert dependent. So it depends on who looks at the pictures over time. And this can change obviously over multiple years when multiple people look at pictures. And as you can imagine, it's quite expensive in terms of human resources and time, especially in the context of monitoring. So to explore a bit more the temporal and ecological dynamics of Vegetoa, IMAS set out to deploy a few cameras underneath salmon farms. Could I have the next slide, please? Oh, the one before. So we deployed time-lapse cameras, which essentially captures pictures right underneath aquaculture cages, so looking straight down at the seafloor at 90 degrees angle. This has a fixed field of view. This was a test trial in many cases, and importantly, these are long deployments, months, and a picture is taken every 1 to 2 minutes. So currently what we have is we estimate percent cover of the indicator of interest, Vegetoa, by overlaying grid, but there can be quite a bit of mistake and error into doing this and touch and go as we've experienced. So that's why having this data set in hand, we set out to say, well, can we have another system or test other methods that would use computer vision given the problems that we have in the context of environmental monitoring? And that's where we reached out to Quan, Mira, and Son. So I'll leave it to Quan for the rest of the presentation.
Thank you very much, Myriam. Hi, everyone. My name is Quan Bai. I'm from UTAS. Myriam gave a very good introduction about the background of this project. And as she said, we just recently started this project about, well, two months ago. And we already received some preliminary results. And I'm very glad we can use this opportunity to share with you. All right. So yeah, it's very in recent years, it's very clear that AI has been very successful in many applications, especially in the field of image processing, or we call computer vision. All right, we have a lot of successful applications showing that AI can help us to do tasks like automated image segmentation, object detection, and also classification. And in this project, this is our goal. What we want to achieve is actually we want to use some AI technology or machine learning technology, which can label the regions with all the bacteria covering area automatically. And we also want to estimate the coverage percentage of the bacteria covered area automatically. Furthermore, we also hope in the next step, we also want to use AI to help the domain people to make a decision. So it's a kind of something like decision support. Then we actually receive a lot of data, labeled data from our collaborator in MS, from Marine and Scott, and also their group. We also identify some challenging issues. For example, the image, okay, the data is actually quite sparse distributed. So which means it's somehow very hard even for human experts, it's not very easy to estimate the coverage, and even for AIs also bring a lot of challenging issues. Another challenging issue is actually from the lighting conditions. So because the image we got actually is from deep ocean, so deep water. So the light condition is not very good. So it's not very easy to identify the bacteria covered area. So it's not easy to recognize those regions. So we just started the project a few months ago, and then we started from two approaches. Okay, the first approach is what we call a grid-based classification approach. Okay, and the second one is called automated coverage estimation approach. right? For the first one, what we did is we separated the image data into a number of grades, okay? And then we ask our colleague from MS to give the labels, to annotate labels. So yeah, I'll just show this one. So something like that, okay? So we ask our colleague in MS to provide labels for each grade. So in general, we have 3 types of grades or 3 types of image fall into the bacteria covered area or region. Okay, the first one, or type 1, is actually a heavily localized region covered by bacteria. And the second one, the type 2, is actually a kind of medium covered region or not very high density region. And the third, type 3, is actually a light covered region with bacteria. We also have another 3 types, the type 4 and type 5 are regions like without any bacteria, but it also has some worm. But in the picture, you can see the worm actually, it looks very similar with bacteria. So somehow it's not very easy to distinguish between worm and worm covered area and also bacteria covered area. And the type 6 is actually a clear area, which means we don't have any worm or bacteria. And yeah, we grabbed a lot of labeled grades from MS colleagues, and then we use a deep learning model to train the machine. And the model we used is called ResNet 50, and this is actually a CNN model with 50 layers. Okay, so we use around 4,761 grades to use as a training data. And after that, we also use around 20,000 grades to validate the model. Okay, so yeah, for the training data means they all got a label. Okay, each grade got a label, but for the validation data, we don't have a label. So which means we expect the machine can tell us which type of grade this image belongs to. Yeah, and we got this is currently some preliminary result we received. So you can see the blue lines, they show the accuracy of the model. And you can see with the training process, the model's accuracy has been improved. And in general, you can see this table also show the accuracy, just show the accuracy of the model. You can see in average, we can get around 80% of accuracy, but this is only with a very small, not a big set of data, only a few thousand, 4,000 something training data, which for deep learning actually is not a lot of training, not a large training data set. Yeah, this is some validation example. You can see this is after validation, we label the grades by using the type, and the other picture just show we use different color to mark the grades belong to different type. Yeah, however, this is only a very preliminary step. One issue we are currently facing is actually we have some unbalanced data, which means we have a lot of labeled grades belong to one certain type, but for some other types, actually, we don't have too many labeled data. So that's why currently we only use a model to do 3 classification, which means that we only detect the region with the bacteria, the region covered by worm, or the clear regions. So we haven't predict the 3 types of different levels of bacteria covered regions yet. But after we got more label data, we believe actually we can do that. So in next step, we are going to apply some fine-grained image classification and to classify all the types from 1 to 6. And also, we are also going to try some other deep learning models. Currently we only try one deep learning model, but later on we also consider to try some other models. Besides that, we also want to use some pre-processing and also post-processing techniques to handle the low quality image, or to process the result we got, to enhance to improve the performance we got. And for the second approach, what we want to do is we want to use some computer vision and also AI technology to automatically detect or estimate the coverage of the bacteria covered regions. So yeah, this is what we did. We also got some image from our MS colleague, and they also actually annotated the image. Actually, not many. We actually got 5 images from them, and they actually noted manually annotate the coverage of the file image. You see, this is we have type 1, type 2, type 3, and also some other types. So you can see each type is corresponding to the coverage of the bacteria. So what we want to do is we want to use, we want to develop what we call non-learning or unsupervised learning model, which can actually detect the coverage or estimate the coverage automatically. So we try a few approaches or technologies. The first one is called thresholding, so which means we use computer vision technology to define a threshold, which can classify all the pixels into 2 groups, black or white. And then according to that, we can actually detect the region covered by bacteria. The other one is called region growing, so which means we have some seed, randomly allocate some seed in the image, and the image will compare the surrounding pixels to see whether the surrounding pixel belong to the same level of the color shade or not. Then actually through this way we can also do image segmentation. The third one is unsupervised learning approach, is k-mean clustering, which means okay, we currently use k equal to 3, so which means we assume actually all the pixels belong to 3 types, which means they are bacteria covered area or worm covered area or clear area. So then we use the machine to automatically to group all the pixels into those 3 clusters or 3 groups. Okay, then eventually we can also achieve segmentation. And the last one, actually, we also use a deep learning model. Okay, what do we call pre-trained deep learning model? But different with the method used in the first approach, or also different with the method introduced by Mathieu. For this deep learning model, we didn't train it. Okay, it has been trained. It has been trained by using some image, in the cloud, which means it's not relevant data. Okay, so we directly deploy the deep learning model and then input our data to see how it goes. All right, and here are some. Sorry, this is the evaluation metrics we used. The first one is called accuracy, which means we try to see whether the predict coverage value or estimate coverage value from machine learning models can fall into the range that the domain expert provided. Okay, so if it's fall into the range, the actual range, then it's true, which means it gave a correct prediction. Otherwise, give zero score, which means it's a false prediction. We also measured what we call center absolute error. So that means that actually that is the sum of the difference between the predicted coverage value and the center of the range of the ground truth. Okay, which is also provided by the domain expert. So we sum them up and see what's the total value of the center absolute error. And here are some preliminary results. So we try all the approach and also input the image, and then eventually we try to see the performance of the model. And here is the preliminary result we got. You can see region growing, which is got the highest accuracy, which is around 60%. And for k-mean, it got actually the best performance in the center absolute error. All right. Surprisingly, actually, the deep learning model without any meaningful training data set, we didn't train the model, but also got something like 40% accuracy. But this is actually the reason why we deploy this model is because later on we also want to use some semi-supervised learning model to train to do that. Okay, and this small demo show you the execution process for us to run the code. So the first one, actually, what we did is we use this is the result we got from the thresholding approach. Oh, sorry, from region growing. All right, the first one is from region growing. The second one is thresholding. And we also changed another image. You can see this one is the original data, and then the next two is the one after we did the segmentation. Okay. Yep. Okay, so next step, what we want to do is we want to use another machine learning model, which is called few shot learning model. Okay, and the reason why we want to use this one is actually this model does not require a lot of training data set. Okay, so we try to use a small set of data or labeled data to train it, and then we want to see what the results can look like. Okay, so far we haven't. We are still working on this one, and believe we will get the result very, very soon. Okay. All right. So this is the members of the team. So we have Scott, Myriam from MS, myself, Mira, and Sung, and also 2 students working on this project. Okay. Thank you very much. These are our emails here, and also we hope we can answer some questions from you. Thank you.
Okay, well, thank you very much, both of you, for that presentation. That was really interesting. We're rapidly running out of time for those of you who are going off to something else on the hour. But there are a couple of questions that we'd like perhaps open it up to the panel. So Neil asked, can this technology be used for fast-moving living objects? And why was this particular bacteria monitored? Myriam?
Well, I can answer the second part of the question. So this is a bacterium that is monitored underneath salmon farms currently, and its presence can indicate an impact, a potential impact because of low oxygen conditions. So it's an ecological indicator, essentially because of its relationship that it has, and that's why it's being used as such. It's not necessarily because of the bacteria in itself. So we can find other ecological indicators that would have the same functions, and for that particular reason, it was well suited to try at least to use computer vision to assess it.
Yep. So, do you want to answer the first question about the fast-moving object?
Yeah, sure.
Well, I think, yeah, we haven't tried yet, but the issue with the model we are using now is very computationally expensive. So for now, I don't think that we can apply it for the fast-moving objects. So that's why it worked very well with with the bacteria, with static coverage object in the seabed.
But there are several architectures. So if we are selecting some lightweight architectures, so yes, we can. It usually takes even several days for training. But once we got a model, and yes, with light architecture, we can. So it really depends. So Son is right. And then also we can find out to use some light architecture to detect moving object as well. Thank you.
I can see Bong Chong asked the question about the recall and also precision of the model. Actually, Song and Mira, we also got the recall and precision of the model, right? So, but we didn't put in the slides.
Regarding what? I didn't get it. So who asked which question?
Bong Chong actually my previous colleague. He asked whether we also measure the precision and recall of the models. Yes, we do.
Yes.
Actually, from the confusion matrix, you can calculate the recall and precision of the model.
Yes.
But we didn't show the number in the slides. Yeah.
Yes.
Here we have another question from Sophie. So how do you know it's just one bacterium alone that you visualize? And wouldn't you have a biodiversity in that biofilm?
We don't. Technically, it's Vegetoa species plural that we see. The reality is that there's been a few studies essentially showing that this is the major bacterium that we see with empirical samples. And that's why it's being used as an environmental indicator. And people have used it with human visual assessment to say whether or not there's an impact. So there's a lot that could be said about the microbial ecology, and there's definitely something, additional projects that go a bit aside from computer vision, but looking at the ecological dynamics of these particular species. But for the purpose of that, this was only to show whether what a human sees, can a computer sees it just as well or better, essentially.
Okay, thank you very much.
Just can I just add to that we yeah, so we monitor for this visually, and someone sits there and scores images, and this process has been developed over time. But down the track, we're hoping to relay the growth of the bacterium to other environmental drivers that we're also collecting images of, and maybe have a more predictive model moving into the future. But at the moment, we're just really looking at, can we automate the process of visually recognizing it? Thanks.
Okay, so I want to probably draw this to a close. It's been a great webinar, and we've had a lot of people, a lot of interest in it, and a lot of questions, unfortunately, we haven't been able to get to. I'd encourage all of you to engage with the Blue Economy CRC Connect portal if you would like to continue this conversation or these conversations. I'd like to thank all of our panelists today and all of our presenters. On behalf of the CRC, thank you very much for taking the time and the effort to present to us today. And thanks to all the attendees for participating and listening in. And I hope, as I said, that you'll start to, if you're not already, participate in the Blue Economy Connect portal, where we can continue these conversations. So I think we'll draw this to a close for the day, and thank you very much.